Alright, welcome to the video on half-life equations. I'm Mr. Lowery, and this video is targeted towards my Chem 1 class, but if you guys are in Chem 1 too, in high school chemistry, then maybe this video can help you out too. Alright, we're working through the nuclear chemistry unit, and half-life is kind of our next challenge that we're facing off against. Alright, a half-life is a measurement of time. And it's a way that we kind of quantify radioactive decay. So we're talking about the time required for exactly half of a radioactive substance to decay. And I have a graph here on the page, and it says that on the y-axis of the graph, so right here on the y-axis, we have molarity, which is a concentration. So it tells me how many atoms are there per liter. And down here at the bottom, we have time on the x-axis. We have time. And the time is also being divided into half-lives. And every 24 minutes, this substance undergoes one half-life. So one half-life of decay. And so that means that the very initially, before any decay has happened, we have an 8 molar substance, and then after one half-life we're down to 4 molar. After another 24 minutes have passed in the second half-life, we would be at 2 molar, and after 72 minutes and 3 half-lives have passed, we would be at 3 molar. Another way of looking at half-life decay would be to look at the percentage that's left. So N, we'll define N as the number of half-lives. So number of half-lives, so what half-life number we're on, and then we'll say the percentage of the substance that remains. So initially, before any type of decay has occurred, we would have 100% of a sample. And then one half-life occurs, however long that half-life is, and 50% of the sample would remain. After the second half-life, we would be down to 25. The third would leave us with 12.5%, and the fourth would leave us all the way down to 6.25%. Okay. So sometimes you guys will be dealing with half-life problems involving the percentage of a substance that remains, and this chart should help you out a little bit on that. All right, we'll move on to the next slide real quick. So we'll go ahead and take a few notes over half-life and solving these problems. Some of the things that you guys will need for this section, you'll need these two formulas. So there's two formulas for half-life equations that we'll work with. One of them says that the final mass, so the mass left after decay has occurred, which we'll abbreviate as M sub F, is equal to the initial mass, so the amount of mass that you started with, divided by 2 raised to the nth power. So divided by 2, because we cut it in half every time, and we cut it in half the number of times of however many half-lives we have, or however many half-lives have passed. So we'll divide it by 2 to the nth because we divided by 2 raised the number of half-lives that have occurred. Then also we have this equation, which allows us to calculate the number of half-lives, and it's the number of half-lives are equal to the total time passed divided by T sub 1/2, which is the half-life length. So I'll write all these down real quick for you guys. M sub F is going to be the final mass, so that's the mass after the substance has decayed. M sub I is the initial mass, so that's the amount of mass you have before decay has started, so at the very beginning. N is the number of half-lives, then we have T, that's going to be your total time, so however long has passed, and T sub 1/2 is going to be the half-life length. So the length of one half-life. So you guys can pause the video if you want to and write these things down so you know what they are. I think one of the biggest challenges that students face in this section is identifying which is which in each one of every problem that they face. So mass is going to be measured in grams or milligrams or some form of that, maybe kilograms if you're dealing with some really big sample. And a way to tell the initial mass from the final mass is that the final mass is always going to be smaller because the substance is undergoing decay. So it's going to be decaying and getting smaller each half-life. So final mass is always going to be the smallest of the two measurements of mass that you have. Your time, same thing. The total time is usually always going to be longer than the half-life length, because usually in high school, especially in these problems, we're talking about multiple half-lives passing before we take a measurement. So the total time is always going to be a longer length of time than the half-life length. So if you're having trouble telling them apart, that's one way that you can do it. All right. On the next slide, I have a couple examples to work through with you guys, and we'll go through those, and we'll identify these individual parts as we do that on the slide. So these individual variables. All right, so we have two equations we said for half-lives, and the two equations that we're working with are that the final mass is equal to the initial mass divided by 2 to the nth power. That's one equation that we had. The other one was that the number of half-lives are equal to the total time divided by the half-life length. All right, and let's go ahead and get our variables out here, and we're going to try to identify as many of these things as we can as we walk through this problem. So a good strategy to use whenever whenever you're approaching a half-life problem is to identify each variable as you read the question. So it says an isotope of cesium, and it's cesium 137, has a half-life of 30 years. So half-life length is 30 years. It says if 1 gram of cesium disintegrates or decays over a period of 90 years, how many grams would remain? So we're wanting to know how many grams would remain at the end. So we're going to be solving for final mass. We're given 1 gram. So 1 gram must be our initial mass. And our total time is 90 years. All right. So we're given these two things right here, 90 years and 30 years. We're given the total time and the half-life length. So that'll satisfy what we need for this equation right here. In half-life problems, as long as you can find the number of half-lives that have occurred, we can always use these formulas to solve the problem. So first step is usually to find the number of half-lives that have passed. And we can do that in this problem by plugging everything into this equation. So n equals the 90 years divided by 30 years. So years cancel out. And we're left with n equals 3. So 3 half-lives have passed in this. So n equals 3. Now, we can use the other equation. So we can use this equation to solve for our final answer. And we do that by m sub f, we're solving for final mass, is equal to 1.0 grams, the initial mass, divided by 2 raised to the nth power, and n is 3. So this ends up being final mass equals 1.0 grams divided by 8, and that final mass equals not 1.25, but 0.125 grams. All right, let's put a box around that. That's our answer for this question. Our final mass is 0.125 grams of this. So on most half-life equations, we're going to be using both of the formulas that I gave you up top. We're just going to be solving for for, and we're going to be solving for the number of half-lives first and plugging it into the other equation. Okay, let's look at one more example. So the next example says that we have an isotope of selenium. It's selenium-83, and it has a half-life of 25 minutes. How many minutes would it take for a 10 milligram sample to decay and only have 1.25 milligrams of it remain? All right, so in this same thing, we're starting off with the two formulas that we need. That final mass is equal to initial mass divided by 2 to the nth, and that the number of half-lives are equal to the total time divided by t sub 1/2. All right, and we'll also define our variables real quick. We have initial mass, final mass, total time, half-life length, and number of half-lives. And remember, we're always solving for n first, so we're going to try to find n before we find anything else after we've identified what we're given in the equation. In the equation, we're given 25 minutes. So 25 minutes is, it says a half-life of 25 minutes. So 25 minutes is going to be t sub 1/2. How long would it take for a 10 milligram sample? So we have 10 milligrams sample to decay. So 10 milligram must be our initial mass, because it's the larger mass that we're given. So that's our initial mass. And we only have 1.25 milligrams of it remaining. So our final mass, 1.25 milligrams. And we're wanting to find the total time, how long it would take for it to decay to that. All right, so since we're given these two this time, we're given final mass and initial mass, we're going to use this equation to solve for the number of half-lives. And we'll do that by saying 1.25 is equal to 10 divided by 2 to the nth. All right. So basically what we're really trying to find in Chem 1 is how many times do we have to divide 10 by 2 until we get 1.25. So 10 divided by 2 is 5 for the first half-life. It would be 2.5 for the second half-life, and it would be 1.25 for the third half-life. So n is 3 in this case. And you can solve this problem using logarithms another way. But for Chem 1 and for the problems that most of you guys are doing in high school chemistry, especially if you haven't had Algebra 2 yet, or something like that, usually we can get by without having to do logarithms here. And we can just realize that 10 divided by what is equal to 1.25? Well, 10 divided by 8 is equal to 1.25, and 2 raised to the nth power is 8, and 2 raised to the 2 raised to the third power is 8, so n equals 3. So we can kind of just think of it like that as well. And that's kind of what we did here, is kind of a shortcut to get by. All right, so now that we have the number of half-lives, so that's not really what they want in the problem, we're going to use that to solve for the total time. So we're going to use this other equation right here. We're going to use this equation to solve for our final answer this time. And we get 3 equals total time, which we don't know, divided by the half-life length, which we do know, which is 25 minutes. All right, so multiply each side by, so times 25 times 25, right? And we get t equals 75 minutes. So 75 minutes is going to be our total time in this case, because this isotope took 75 minutes or 3 half-lives to decay from 10 milligrams all the way down to 1.25 milligrams. All right, sorry, this is kind of a lot to show on one slide, but hopefully if you guys need to, go back and pause at any section that you have trouble with and review it over and over until you can kind of get the process down. All right, so on the homework, you may have to solve for initial mass or final mass or time or half-life length. But you can use these two examples as kind of a guide to get you started. Just stay organized on it, identify your variables like I did over here on the left side, and plug them into the equation depending on which two you're given, and you should be good to go. All right, so thanks. If you guys need any help, send me an email. Appreciate it.